Liquids and Solids, Part 3. The objectives: calculate energy changes when a phase changes, discuss the setup of phase diagrams, predict the phase of a substance using a phase diagram, explain the terms critical temperature, critical pressure, triple point, critical point, and supercritical fluid. These are the changes of state that we're going to investigate: subliming and depositing, melting and freezing, boiling and condensing. Sublimation and deposition. Molecules in a solid vibrate. Surface molecules with sufficient energy may break free from the surface and become a gas. This process is called sublimation. The capturing of vapor molecules into a solid is called deposition. The solid and vapor phases exist in dynamic equilibrium in the closed container and temperatures below the melting point. You can see that down here, these are opposite processes, but energy is always involved in going in either direction. Ice can sublime under certain conditions when it goes directly from the solid state to the gas state, kind of skipping the liquid state. I'm going to see what will cause this to happen a little bit later. Next question: does the temperature of a solid change as it melts? How much heat is needed to melt a solid? Well, here's a piece of ice, and you can see here that the temperature of the ice when it's melting is 0, and the water that it produces is also 0. So the answer to the first question is no, the temperature doesn't change when it's melting. This is true for a crystalline solid, not for an amorphous solid. In order to calculate the energy involved in the phase change, we're going to use the heat of fusion times the mass of the substance anytime we have something melting or freezing. Now for water, the heat of fusion is 80 calories per gram, or we can use 6.02 kilojoules per mole, whichever is more convenient. Here's a definition for the heat of fusion: the amount of heat energy required to melt 1 mole of the solid at its melting point. Notice the symbol for heat of fusion is delta H with FUS, kind of a subscript. Enthalpy refers to more than just heat, but we'll see enthalpy of fusion later on when we do thermochemistry. And the reaction is always endothermic, meaning that in order to melt anything, you constantly have to be putting energy into it, and therefore we have a positive sign. Here's a chart comparing 4 substances and their heats of fusion along with the melting point. Now, earlier we looked at substances in terms of melting and intermolecular attractive forces. And I think what we saw here was water. Water is very, very polar and has the highest melting point of all these compounds listed. Rubbing alcohol is a little bit polar and also non-polar, and its melting point is much lower. Acetone is also polar, but it shows no hydrogen bonding, as we saw with water. We have a little hydrogen bonding with isopropyl alcohol, and that's probably why its melting point is a little bit higher than that of acetone. And diethyl ether, is non-polar, and it has a much lower melting point. All right. How about calculating this? How much heat in kilojoules is needed to melt 15 grams of ice at 0 degrees centigrade? I'm going to convert my mass to moles, and then I'm going to use the kilojoules here. We had earlier to get kilojoules for my answer. Here's my setup. So the 15 grams was given in the question. Here's my molar mass, so I'm going to be dividing 15 by 18, give me the number of moles, and then I'm going to multiply that answer by 6.02. We'll see everything that'll cancel out here. Should work out pretty good. And I get an answer of 1.20 kilojoules, which makes sense. Let's check out another phase change. So here we have water, and we're boiling the water. You can see the water boiling here, and 100 degrees we're seeing on our thermometer. So does the temperature of water change as it boils? Most people think it does, but as you would find out, it doesn't. It stays constant. In fact, anything you're cooking in water can only be as hot as the water is. That's why the hotter the water becomes, the faster foods will cook. So we have water at 100 degrees is becoming steam at 100 degrees. In order to calculate the heat involved in this phase change, we need the heat of vaporization. And for water, it's 540 calories per gram. Now, if we have water in terms of moles, we can use a different value for that, and that's 40.7 kilojoules per mole. And here's the same thing we saw a moment ago. Okay, let me skip right over to heat of vaporization. And so heat of vaporization here is the amount of heat energy required to vaporize 1 mole of a liquid. And it's going to be at its boiling point, though. It should be saying that. Here's our symbol for heat of vaporization, delta HVAP, and sometimes called the enthalpy of vaporization. And here are the values listed. So here for these same 4 substances again, we have the normal boiling point. Now we'll see later, what's normal mean? And then we have heat of vaporizations in both at the boiling point, and it says heat of vaporization at 25 degrees. Because yeah, liquids will vaporize at all temperatures. So normal boiling point for water. Let's see what we have. We saw earlier, boiling points are becoming lower, which means the intermolecular attractive forces are weaker as we go down. We saw that with melting point. Heat of vaporization at the boiling point, the highest is water. The next is the alcohol. You notice these are going down, same way these are going down. So this is giving us a good idea about intermolecular attractive forces as well, because you're separating these molecules from each other, which means you're overcoming those intermolecular attractive forces. And these values are different at 25 degrees. So at 25 degrees, they don't have as much energy as these molecules here. That's why you notice these numbers are a little bit higher. Here's a problem for you to try. How many kilocalories I needed to change 50 grams of water at 100 degrees to steam at 100 degrees? So to do that, we're going to use our equation mass times heat of vaporization will equal the energy. And we set it up. Here's 50 grams of steam, and I'm going to use my 540 calories per gram. Then I'm going to convert calories to kilocalories, and I get 27 kilocalories for an answer. And everything will cancel out very nicely. So here's a heating curve, and it can be for really any crystalline substance. You notice we wind up with 2 plateaus, and we have 3 diagonal portions. In order to calculate the energy needed to melt a solid or freeze a liquid when it's at its melting point, we use an equation that we saw a moment ago. What about if we just have the liquid changing temperature? Then you notice we don't have a value called the heat of fusion. We have to use these 2 values, which are change in temperature and specific heat. If we're right at the temperature to change the liquid to the gas, or at the boiling point, we can use the heat of vaporization times the mass, as we saw a moment ago. Make sure we get everything there. Yeah. So what you want to note is that we have 2 equations for changing phase, but only one for changing temperature. Now what about these other 2 diagonals? We could use the exact same equation here, but would have a different specific heat, depending on whether it's the gas state, the liquid state, or the solid state. You probably have to use these in one of your labs that you're doing this semester. Okay, let's check out phase diagrams now. One of the objectives you have was to be able to define the terms that are coming up, so you might want to jot these down. Critical temperature, the temperature which above a substance cannot exist as a liquid no matter how much pressure is applied. Every substance has a critical temperature. So what we're going to see is temperature and pressure kind of affect each other in determining what the phase is of a substance. So a critical temperature, the highest temperature something can be at, where you can change it back to a lower phase by just using pressure. Critical pressure, the pressure required to liquefy a substance vapor at its critical temperature. Critical point, the endpoint of the pressure temperature curve that designates conditions under which a liquid and its vapor can coexist. At higher temperatures, the gas cannot be liquefied by pressure alone. At the critical point, defined by the critical temperature, T sub C, and the critical pressure, P sub C, phase boundaries vanish. And then the triple point, the temperature and pressure at which the three phases, gas, liquid, and solid, of a substance coexist in thermodynamic equilibrium. I want to point out right up here, when they talk about boundaries vanishing, we enter what we call a supercritical fluid state, and we're going to see that coming up. Here is a typical phase diagram. So let's check it out. We have the solid, the liquid, and the gas state here. And we have these three lines. So let's say for a solid to the gas, remember that's sublimation. So sublimation is going in this point like that. Deposition going in this direction. So as we go to the right, the temperature is increasing. So the warmer something becomes, the greater the likelihood that it would be, let's say at pressure here, that is likely going to be a gas. The triple point is that temperature at which the liquid, the solid, and the gas state exist in equilibrium. Going across this line, we have the melting and the freezing point. So we could drop down and see what the melting point is for a particular substance right to here. Here we have the critical point, the highest temperature at which the liquid, the gas, well, really just the liquid and the gas can exist. But above this point, we enter what we call that supercritical phase. We're going to see that. Now it's a little bit better, I think, with this diagram because we have some numbers in it. So this is water. So we already know that at normal pressure, let's say 101 kPa is the normal atmospheric pressure. So let's follow this line across. So if we go across like this, and we hit this point, which is the ice-water barrier, and we look down, we get the normal melting point of ice. This is also the normal freezing point of water. Now the triple point, which is just about the same temperature, that's the point at which all three of these phases can exist at the same equilibrium point. So in other words, at the triple point, the same number of water molecules are vaporizing as are freezing, and the same number of frozen water molecules are vaporizing as are depositing. So we can go in all these directions. Now we can see as we continue to increase the temperature, but we stay at normal atmospheric pressure, the tendency to become a liquid starts to vanish. And right when we reach 100 degrees centigrade for water, we're at the boundary where water will spontaneously become a gas. And above 100 degrees centigrade, still at 101 kPa, now you're in here, then we're saying that the normal phase for water is actually steam, has its own name. So what happens if you can keep increasing the temperature of the steam gets hotter and hotter and hotter. Now you can take, even if you're right here, you can increase the pressure and actually change that steam back to liquid water. And this is what happens in a pressure cooker. So in a pressure cooker, you use the pressure of the steam that you're creating to force itself to go back to a liquid, and therefore you wind up with water in the liquid state inside your pressure cooker that's well above 100 degrees. It might be 125 degrees centigrade. And therefore food cooks a lot faster in that water in the pressure cooker because the water in the pressure cooker is at a higher temperature. And notice we can't get beyond that point. Once the temperature gets beyond 374 centigrade, we enter that supercritical phase where no change in pressure can make that gas change to a liquid. Now here's some applications of all these phase diagrams. Freeze-dried foods, like this ice cream here. I know they used to sell this at some movie theaters. How do they produce that? They dehydrate it by sublimation at pressures below the triple point of water. So as they lower the pressure, instead of the ice that's inside that ice cream melting, it vaporizes. And here's your ice cream here. The immense pressures beneath glaciers result in the partial melting to produce a layer of water that provides lubrication to assist glacial movement. So in other words, glaciers can move because they're so heavy. And even though the temperature below them can be below zero, because they're so heavy, they lower the melting point of the ice, and the ice melts, and so the glacier can move like that. Now, supercritical fluid, I mentioned this earlier. A liquid is heated in a sealed container, more vapor collects, causing the pressure inside the container to rise, the density of the vapor to increase, and the density of the liquid to decrease. At some temperature, the meniscus between the liquid and vapor disappears, and the states commingle to form a supercritical fluid. Supercritical fluids have properties of both gas and liquid states. Now here's an example here. I know there's a video on YouTube that shows this. We have the gas, then we have the liquid down here. And what happens as we increase the temperature, and you can see the liquid is boiling, more liquid is becoming gas. And at some point in time, we reach the temperature at which that liquid is boiling, and we wind up with all our gas up in here, but we still have the liquid state down here. And if we increase the temperature above that, we wind up making that supercritical fluid. Now, we're not measuring the pressure, but you see the container walls. Since the container can't get any bigger, the more pressure we make, the higher the pressure is above both the liquid and the gas. And so that line between gas and liquid disappears. So here we can see it. We have a phase diagram for carbon dioxide. So we all know carbon dioxide is a gas to us. And why is that? Because kPa, this is again the normal atmospheric pressure. And if you just follow that temperature line, and you get like right around here, this would probably be like 25 centigrade or so. And 25 centigrade is, let's say, about 80 degrees Fahrenheit. So CO2 is a gas. Can you change CO2 to a liquid at 25 degrees centigrade? Well, you can, but you'd be right at that point there. And look at all the pressure it would take. About 10,000 kPa, which is about 100 atmospheres. That's phenomenal. But what about frozen CO2? Well, let's go look at that now. So that happens about minus 78 degrees centigrade, which would be, this is minus 75, so minus 78 would be about here. So yeah, we can go from the solid to the gas directly at normal pressure. And so that's what happens to dry ice. Dry ice is in here, and it goes directly from the solid to the gas state. And again, that's called sublimation. Now, in order for that solid to actually melt, in order for it to do that, the pressure has to be tremendous, and we just don't see those pressures. Now, here's a good example of the usefulness of that. How do they make decaffeinated coffee? Well, at one point in the beginning, they used to actually add a chemical to caffeinated coffee that would take out the caffeine. But then they complained that some of the residuals from those chemicals they were adding wind up in decaffeinated coffee. So now what do they use? They use CO2. So caffeine molecules, which are pictured here, have both polar and nonpolar regions. The red represents oxygen atoms. So here, this is going to be your polar region here and here. And all this big thing over here, this is nonpolar. They can get soluble in solvents of varying polarities. Now, the schematic shows a typical decaffeination process involving supercritical carbon dioxide. So to make supercritical carbon dioxide, you have to have carbon dioxide, remember, at a very, very high pressure. So let's see how we start. We start off with the soaked coffee beans in here. We have our extraction vessel, and what they have is in here supercritical CO2, and that forces the caffeine out. So coming out of this container, we have the CO2 and the caffeine. And what goes in here is that combination goes into the bottom here, and then water is added, and then the caffeine in the water, because the caffeine will dissolve in the water, exit in this direction. And what goes up at the top here is just that supercritical CO2. And that comes back into that extraction vessel to be used over and over again. So you have to have the CO2 in there constantly sealed up. Otherwise, you wouldn't be able to keep it as a supercritical fluid. Okay, that is the end of the video.